Street. Let me maybe get the right school logo up there. There we go. Okay, welcome back after a couple of weeks break. I've taught you just about everything you need to know for CET236. Right. Can everybody mute? Drew,
Sorry
can you?
to interrupt. I think you're muted.
I'm muted, am I? Okay, thank you. Okay, so this is CET. Can everybody mute, please? Thank you. Drew and Ryan, can you mute? Thank you. So this is welcome back. We've got. I was just saying while I was muted that I've pretty much taught you everything you need to know already in CET236. The only thing that we need to do now is to add complex resistances called impedances to the mix. And that's why I'm going to introduce today capacitance and inductance. Bishel, can you mute, please? So let's just see where we are. All right, we've got a few weeks left, and we have another midterm that's going to that I've released, and I'll talk about that briefly. And we have the final. So the second midterm and the final are going to be oral in nature, and I haven't finished setting the final yet. I want to try and do the final the way I've done some other finals, not in circuit analysis, and I'm not quite sure on. I'm not quite sure the pattern fits. It fits really well where I teach in other subjects, but the way I'm thinking of doing it here, I'm not quite sure it fits, but we'll see. So we've effectively covered all the left-hand topics, and pretty much, Alex, can you mute, please? Pretty much everything is on the right hand side is stuff that we need to cover, but it's all pretty much just replacing our real valued resistances with complex valued ones. The only slight caveat to that is transient analysis is a little new, so we will talk about that. Probably not this week, probably next week. So that's the assessment calendar, and I've had a couple of requests to move one or more of the assessable items due today off, and I'm okay with that, given that we've got effectively got a break next week. So I don't know which ones you want me to put off, whether you want to put the lab off until next week, or the homework 7 maybe, or maybe the lab and homework 7. Does anybody have any preferences one way or the other?
Yeah, I think lab 7 and 7 for next week.
Okay. So while we're here, let me just go do that. That's the wrong course. Let's go to the right course. So labs and lab 7, we can certainly put that off. So let's edit it. And current due date is today. We'll make it the 17th. And we'll cut off access on the 17th as well. Okay, so let's just have a look at the live assessment calendar. Okay, so that's the yellow one here is the, don't know if we can make that any bigger. Maybe. Right, so the yellow one here is the today's date, and I've just moved that lab, which is lab 7, off until next week. Okay? Is that giving you enough breathing space? It does space things out a little better, I must admit. I did leave a bit of a gap between the last few real valued only assignments and the assignments coming up, which are about complex valued ones. Okay. So, oops, let's go back to OneNote. So what I've just done is I've moved that lab 7 to be due next week. So that should make life a little more bearable, perhaps. So just when you thought it was safe to go back, I've released the second midterm. And the second midterm only has 2 topics. It has mesh analysis and it has nodal analysis. And each topic I've released 2 questions. And the aim is for you to answer, tell me while we're on the Discord call, how to solve each one question from each topic. So 1 question from mesh analysis and 1 question from nodal analysis. And then I'll, you talk me through your solutions. There's only placeholders for the different resistance values and voltages and currents. You to talk me through how you would go about solving it. And just like the first midterm, I need you to explain in a certain amount of detail how you go about it. And it's basically making sure, for example, in mesh analysis that you define all the current directions to start with. In nodal analysis that you define all the nodes, although in these questions the nodes are already defined. But then you need to define all the element currents and their directions. That needs to be expressly said during the midterm. Kyle, can you mute, please? Thank you. That is open. I noticed I've already had 3 or 4 people book, and I've forgotten how long I gave you to do the, where's it going there? But basically we're running up against, it's not going to let me go there. We're running up against the end of semester, so basically I would like you to try and get it done by the end of April. So we've got another 20 days in April, and I think there's enough time slots available. So you want to put homework 7 in the, move homework 7 off. Like I said, I'm okay with that. Let me go edit that assignment. I will do that too. So that's currently due on the 10th. Let's move that one off to the 17th. Sorry, I didn't see the chat until just now. Okay, let's just check the assignment calendar is set up correctly now. So there we are, both homework 7 and lab 7 are put off. So hopefully that'll, oops, let's just go back and make that annotation as well. So the superposition homework is also moved to here. I can go over any of the problems. That's we'll wait until we get there. I've got a. I just want to finish off with the midterm, but yes, I'm going to spend some time today asking if anybody has any questions about the open homeworks and the open labs. So once we get there, Giovanni, ask away. Okay, so that's pretty much all I've got on the list for today. I do want to introduce the capacitance, impedance, reactance, and that should, it's actually, I don't know why I typed that twice, that should say inductance, not impedance twice. Yeah, funny I didn't, it's amazing what my head thinks and what my fingers type are not necessarily the same thing. Okay, so I'm going to go straight into the capacitance, impedance, reactance, inductance piece. And once we've done with that, I'll ask for questions for homework 6, homework 7, and then the labs. Okay. So I've put topic 10 in here. And again, so this is the key difference between what we've done to date and what we're going to do is that we're going to move from just using R, which is the resistance in ohms, to using Z, which is the impedance. In ohms. And just like we had V equals IR, we're now going to go with V equals IZ. And Z is made up of the real component, which is the resistance, plus the imaginary component, which is called the reactance. And it's usually denoted X. And that's the resistance. Okay? So the other thing we're going to change is previously we would have V equals 10 volts, or V equals 18 volts, or V equals negative 3 volts. But now we're going to change that so that all of our voltages and currents are sinusoidal or cosinusoidal. So they're going to be of this form, right? V of t is A times cosine of omega t plus theta, right? And A is the amplitude, sometimes called the peak voltage, omega, that's little omega, that's the frequency in radians per second. Theta is the phase. And let me just write theta down. Sometimes I'll use the other Greek letter phi or phi, also for the phase. Okay, and in this case, if we've just got a resistor and we apply a cosinusoidal voltage V of t, well, Ohm's law still applies, even though now instead of having a constant voltage like this one, we've now got a time varying voltage, right? It depends on time. But it's still, Ohm's law still applies. Just because we're changing the voltage doesn't mean that Ohm's law changes. Right? So we can figure out what the current is by just dividing the voltage by the resistance, right? I equals V on R, which is what's happening here. And this is a little bit of notation. What we're going to do when we talk about resistive, inductive and capacitive circuits is we're going to essentially elide away. We're going to remove the fact, at least from what we write down, that that the circuit is being excited by a cosinusoidal signal. Right? So that's what we're doing going from here to here. We're saying, okay, we know the system is running at frequency omega. That doesn't change, but the only thing we're really interested in is what the phase and amplitude is. So we go from this complicated looking way of representing the voltage to something slightly less complicated, right? And this notation here is called Phasor notation. You might recognize it as polar notation, right? You've got the amplitude where, well, we've effectively A is the amplitude, but we're using a unit amplitude vector, and here is the angle of our polar notation, right? So the usual polar notation is amplitude and the angle in this angle sign. And then we can just, because we've got these two just cancel out, right? Remember from our complex numbers, we can write that in this notation in exponential form rather than polar form. And therefore we've just got a e to the j theta, or 1 e to the j theta divided by 1 e to the j theta here. So those two we can just cancel out. And that is exactly what we've been doing all along. Except now I'm talking about having a cosinusoidal voltage and current instead of just a constant voltage and current. So, capacitance. So we haven't really come across a capacitor yet, but a capacitor is a circuit element that looks like that. And the reason it looks like that is the way you make a capacitor is you have two conductors separated by a dielectric, and one dielectric is air, so it's perfectly possible. It could be an air gap. Most capacitors that you actually see use other materials for dielectrics. Electrolytic capacitors use a fluid or a paste. Ceramic capacitors, funnily enough, use a ceramic. I don't know if any of you have ever seen any of the old crystal radio sets where you had a tuner capacitor. Those tuner capacitors, let's see if I can find a picture. There we go. Right, so there's an old crystal radio tuner capacitor, and you can see that there's just lots and lots of metal plates. Right, lots and lots of metal plates separated by air, and you can turn the knob there, and what effectively happens, let me just get myself a bit better set up for, where's it gone? I normally have that one there, and then I usually have that one there. That's better. What normally happens is as you twist that knob, there's more overlap between the different layers, and as you twist it the other way, the overlap becomes less, right? So you change the area of overlap between the separated plates, and that changes the capacitance. All right, just looking at... Okay, let's go back here. Right, so we've got a capacitor. Now, one of the things about both capacitors and inductors is that the relationship between the voltage and the current is a bit different. Right? We don't just have that direct V equals IR as it's stated. We can get back there, but the relationship between the voltage and the current for a capacitor is a derivative relationship. I equals C dV dt, right? Where dV dt is the derivative or the slope of the voltage at the given time, and C is the capacitance of the device. Okay, so again we can excite the capacitor with a cosinusoidal voltage. And well, actually, before we do that, let's think about what happens if we apply a constant voltage, right? What happens if we apply a constant voltage? Oh, I don't think my don't think my My bot's running. Oops, it's not going to run. Okay, so I can't bingo. Oh well. I had to do a complete revamp of my machine, and I forgot to check that my Python was set up. So let me just pick on somebody. I could just do that, couldn't I? Christian, any thoughts on what would happen if I apply a constant voltage to a capacitor?
I would say it could store some of that voltage into the capacitor.
Right, it'll store some of the voltage. What will the current be?
Maybe the value of the capacitor times the voltage, if it's directly related to the same formula that we have for Ohm's law, but instead of the resistance, the capacitance, maybe.
Well, I said that the relationship is here, right? So I equals C dV dt. And if we take dV dt of a constant voltage, then that's always zero. Now it's a bit of a trick question, because one of the things we've got to talk about a little later is a thing called transients, because the capacitor, before you connect the 10 volts DC, the constant 10 volts voltage, the capacitor will not have 10 volts across it. So there's a bit of a transient analysis you've got to do when you connect it straight up. But if the voltage source of 10 volts, constant volts, has been connected to the capacitor for some time, and we'll define what some time means a little later when we talk about transients, then the derivative of the voltage is zero, because the slope, right, it's just 10 volts. It's constant. Okay, that's not constant, but I can't draw a straight line apparently. But it's just a straight line, right? So there's no slope. So the current flowing when you connect a DC voltage, a constant voltage supply, up to a capacitor is none, is zero, right? Because of that I equals C dV dt. Okay, so we can actually plug that V of t in there, right? And because we know that the derivative of cosine is minus sine, and if the derivative of cosine omega t is minus omega sine omega t, so we can just look that up in a derivative table, right? So there's our dV dt. So our current is just minus a omega c, because we've now got I equals C dV dt, we've got dV dt, we can multiply it by c to get the current. Okay, and then we can do something like what we did before with the resistor. We can try and figure out what the impedance of the capacitor is by putting the voltage over the current. And this is where we get to move from having the omega t component there to not having the omega t component, right? So here's our voltage. Here's the current that we figured out. And then just to make things a little easier, we want to try and have the cosine on top and bottom with just a different phase, maybe because of the sine. And then we can do that shift from V of t, or I of t, into polar or Phasor notation. Now I keep reiterating the word Phasor because I had somebody complain to me about a year ago, maybe a little longer, that I had never taught phasors in this course. I cannot teach this course without talking about phasors. I think the problem was I didn't actually use the word phasor much. So I'm going to, since then, I've been overusing the word phasor. Right? Phasor is the polar representation of the cosinusoidal or sinusoidal voltages and currents. So I'm going to continue to overuse it just to make sure you get the word phasor. Right, and then that makes this a little easier to deal with, right? Because we know that they're just polar, it's just a polar representation. So, and we know that dividing one polar representation by another polar representation, we just take the ratio of the amplitudes and we subtract the denominator phase from the numerator phase, which is what we're doing here. Okay, and because we've got theta there both times, we just end up with 1 angle 90 and 1 angle 90 is just J, right? If you remember your real and imaginary components, and we're going up 90 degrees, and if it's got an amplitude of 1, then that is just J. Remember, I'm using J for the square root of -1, not I, just to confuse the mathematicians amongst you. The real reason I'm using J instead of I is because, as you've seen throughout this course, we use I in electrical engineering to represent current. So we needed a different symbol. So for complex numbers, so we're using J. Okay, and then that just simplifies to this. So we can very easily find the impedance, the complex valued resistance. In fact, it's a reactance. It's imaginary only, of a capacitor. The impedance of a capacitor is either minus J on omega C ohms or 1 on J omega C ohms. I tend to prefer the second one, but either is fine. 1 on J omega C. Now let's look at what happens when we go back and think, well, how does that relate to the question I asked before about a constant voltage, right? If we've got a constant voltage, then omega for a constant voltage, right? So for V equals 10 volts, say, then omega is 0. right? And what that says is that ZC is 1 on J0C, which is effectively minus infinity. So if the impedance is minus infinity, that means, you know, I equals V on Z, we're not going to get any current, which matches what we thought about when we talked just about the capacitor, the voltage current capacitor relationship in terms of a derivative, right? So we've simplified the analysis of a circuit involving a capacitor by ensuring that the circuit is just running at omega, and we've effectively not forgotten about it, but we've said, okay, well, that everything is running at omega, so we don't need to think too much more about it. So we get a nice relationship, right? We still get Ohm's law, but provided we know we're running at a particular frequency, then we can figure out what ZC is, and we can get a relationship between the voltage and the current through ZC. Any questions about that? Okay, I'm going to move on. So we've got another new device, and this new device is called an inductor. And an inductor is drawn just like a coil, because that's all it is, right? It's just a coil of wire you sometimes wrap around a core, and that's pretty much it. So again, let's think about exciting the coil, the inductor, with a cosinusoidal voltage. Well, the relationship between the voltage and the current for a coil is this one. It's an integral relationship. You can either, well, you can write it as a derivative as well. It's I equals 1 on L times the integral of the voltage. The other way to write it, right, is V equals L di dt. So let's think about what's the best way to do this? So let's think about what happens if we apply 10 volts, constant 10 volts to an inductor, right? Well, Jonathan, any thoughts on what would happen if we applied 10 volts to an inductor? No response? That's okay. You can type it if you're quick enough. You don't know. Okay. How about Saray? Any thoughts on what the current might be doing if you apply a constant 10 volts to an inductor?
No, I'm not sure.
Okay. I'll give one more person. How about Drew? Drew Tingley. Any thoughts?
No, I don't really know.
Okay. So let's just plug it into the equation, right? I of t equals 1 on L times the integral of 10 dt, right? And if you integrate a constant, now normally you've got to have limits to the constant, so that it's basically going to be 10t plus a constant. And that doesn't quite get there, but an ideal inductor has zero resistance. It is just a wire. That's the way they're made. They're made from wires. And I wonder if I might have one over there. I might see if I can grab it. So if you connect up a voltage source to a wire, what you get is either a heater or a fuse, because it'll if it's got zero resistance, it's going to try and pull infinite current, right? V equals IR, or I equals V on R. If R is 0, it's going to try and pull infinite current. And that's what that integral is telling you, right? As time goes on, the current keeps getting bigger. So in order to be sensible, you need to have a cosinusoidal voltage applied to an inductor. In fact, let me just see if I can find, I may have one over there. Yeah, there we go. Yeah, so this is a really old board, and I got the wrong logo there. Let's get the right logo up. There we go. So this is a really old board, but where are we? If you can see, if you can see in there, they're a bit out of focus, but those two pink things there, they're little toroids, little donuts with just wire wrapped around them. And then there's another one that, and it's a bit hard to see. I might see if I can take a photograph and share that. That might be a bit better. So let me just take a photograph, and that might be a little. Yeah, that's better. Let me just share that in the CET. I thought there was a CET materials channel, but apparently there isn't. Go there. Yeah, so let's see if I can open that link up. Right, so there we go. So that's those two little toroidal cores just had wire wrapped around them, and they were two little inductors that I used in that circuit. Right, so that's kind of cool. Okay, so that's all an inductor is. It's a wire, sometimes wrapped around a core of usually ferrite type of material. Okay, so let's have a look. Let's do the same thing we did for the capacitor. Right, so oops, it's just my phone coming in. I reconnected it, and it likes to upload all my photos and tell me where it's uploaded them. Right, so if we integrate our A cosine omega t plus theta, we get A on omega sine omega t plus theta. So if our voltage is A cosine omega t plus theta, then we get our current is A divided by omega L sine omega t plus theta. And then we can try and figure out what an impedance for our inductor is by dividing the voltage by the current, just like we did before. And just like we did before, we need to go from here to here. We want cosine on both the numerator and the denominator. We just use the phase shift relationship between cosine and sine to do that. And then so that's the cos sine relationship. And then here we just do use phasors, because we know everything's running at omega t. And so we just use the polar notation. Once we've in the polar notation, we can just write it out a bit more simply. And that means we get our final result, which is that the impedance of an inductor is equal to J omega L. Okay, and again it's in ohms. Impedance and resistance both have the same units. They're in ohms. Capital omega as the unit denoter. Okay, any questions about inductors? I thought, since I brought up capacitors, the other part of a crystal radio set is the inductor, right? Because you actually need the capacitor and the inductor in order to, but usually the inductor is not tuned. Right, there's a nice example of a, maybe, there we go. Right, so here on this one, maybe they are tuning it. That's kind of cool. So here, this is a crystal radio, and you've got the capacitor there, which is just a fixed, it looks like it's a poly capacitor, right? And you've got a diode there, which is the crystal part of the crystal radio, and here you've got an inductor, right? Which this one's got a lot more wires than the example I had up on the screen earlier, right? But it's all very very much. Let's see if I can make that a bit bigger. There we go. Right, it's all just a. Oh, I see. So they're tuning the inductor this time. Usually you use one of those vaned capacitors, but they're tuning the inductor by just running one end of the inductor up and down the length of the coil. The other end is fixed. Okay, it's kind of cool. Okay, so now you should be able to solve all the problems I give you with inductors and capacitors and resistors in them. That's all you need to know. It's a little, there's a few other things we need to do, but let's just have a look at the summary. Right, the summary for impedances of resistors, inductors and capacitors. The resistance of all three of them is R, 0 and 0. Capacitor has 0 resistance. An inductor has 0 resistance. The reactance of a resistor is 0. It doesn't have any imaginary component to its impedance. The reactance for an inductor is omega L, and the reactance for a capacitor is minus 1 on omega C. Remember, reactance is a real valued thing, but it is the complex, it's the imaginary component of the impedance. So that's why when we combine resistance and reactance together to get impedance, we get the resistor's impedance is just R plus J naught. There's no complex component. The inductor's impedance is 0 plus J omega L. There's no real valued component to the impedance of an inductor. And the capacitor impedance is 0 plus 1 on J omega C. Again, there's no real valued component to the impedance of a capacitor. So the units of resistors are just ohms. The units of an inductor, before we get to its impedance, the units of an inductor, the units of L, are henries. The units of capacitance, before we get to impedance, the units of C are farads. And then we can also talk about the inverse relationship, or the inverse thing. So the inverse for resistance is conductance, and the inverse units are Siemens. The inverse units for henries is of inductance is reluctance, and the inverse units for capacitance is elastance, right? And then the units are, sorry, the name is reluctance and elastance, and the units are inverse henries or inverse farads. I've heard people use YRNEH and DARAF, so the reverse of Henry and Farad, but I prefer just to say inverse. Okay, so let's do some examples. All right. So here's a circuit, and we've got a voltage which is 4 cosine 10,000 T plus 45 degrees. And we have a resistor, and we have an inductor, and we want to measure the output voltage, which is the voltage across the inductor. What should we use here? Joel, do you have any thoughts on how we should approach this problem?
Not really sure where to start off.
Okay. Mike Fedora, any thoughts on where to start off?
My best guess would be to figure out the voltage and amps going through the first resistor, and then just plug what you get into the formula for the next part, I guess. Not really sure.
Okay. I'll give one more person. David Dubac, any thoughts on how we approach this problem? So let me just restate it. What would happen if I redrew the circuit like this? David, would you care to hazard a guess? David Dubac? Okay, so how do you find the current in the inductor? Stephen's just typed in the chat. So I think about it like this, right? So if this was just R1 and R2, right, we'd know that the output voltage, now because of this is upside down, it's going to be minus VI times, and it's going to be, just use the voltage divider equation, right? And this question is no different. The tricky part is that, well, for a start, VI is upside down, so we've got to think about it a little differently. But the tricky part is we currently have only the inductance of the coil. L is 100 microhenries. So the first thing we've got to do, every time you come across one of these questions, the first thing you have to do is to turn all of the capacitors and inductors into impedances. Right, and here we've got an inductor, and we know that ZL, the inductance, the impedance of an inductor, is J omega L. So here we know L, we know omega, so that's going to be J times 10,000 times 0.1, right? That's 100 by 10 to the minus 3, which you could write out as 0.1 henries, right? So that means our ZL is J 1000 ohms. Okay, so that's the first piece. the second piece you've got to do is, we really don't care, now that we've used the frequency to find the impedance, we really don't care that we've got 1000 T. Right? So what we want to do is we want to transform VI into its Phasor notation. Right? So its amplitude is 4 and its phase, its angle is 45 degrees. So there's the Phasor representation of the voltage. And now we should be able to write out, not quite as direct as that, but we should be able to write out the expression for the output voltage, right? The output voltage is equal to, now, I'm going to, because this is upside down, I'm going to assume that that's that, and we've got that, right? So then the output voltage is -4 angle 45 times, so the output voltage is, the voltage divider equation is ZL, which is J1000, divided by ZL plus ZR. And ZR is nothing but R. Okay, so there's our, and I forgot to start up MATLAB. Let me just go do that. Wherever MATLAB got to, there it is. It is starting up. Okay. Okay, so that will tell us how to get the out. Let me just wait for MATLAB. Where have it got to? Where's it gone? There it is. Ooh. Ooh, that's interesting. I've got that there and there. Okay, let me just make that less than full screen so I can see MATLAB at the same time. Okay, so this is Vout equals -4 times, now remember with polar coordinates we need to use, in MATLAB we need to use the exponential function, right? Because we can write down 4 angle 45 degrees as 4 times exponential 45 degrees in radians, right? So, but I need to actually, I need to multiply it by, I think it's 1J is MATLAB's version of J, and then I need to multiply it by the angle, but the angle needs to be in radians. Okay, so that's actually my, that's not V out, that's V in, right? So there's my V in, minus 2.828 minus J 2.828, and MATLAB uses I, so I'm gonna say J anyway. Right, and then our V out is equal to V in times J1000 divided by J1000 plus 1000. Okay, so there's our V out. So our V out is equal to minus 2.828 minus J 2.828 volts Or the other way to write that, let's just do it up here. So that's, let's just draw our real and imaginary axes. So minus J 2.82 here, right, is down here on the imaginary axis. So that means that you can either think about that as plus 270 degrees or minus 90 degrees. Right, so our V out is equal to 2.828. Let me give myself more room. So our V out is 2.828 cosine 10,000 t, and I'm going to use minus 90. And that is in volts. Okay.
Could you repeat how to go from the minus 445 degree polar notation to the rectangular imaginary notation?
Sure. So, right, so we have A angle theta, and we want to convert from polar or phasor notation to rectangular. And the way we do that is through a thing called Euler's formula. And Euler's formula says that A e to the j theta, provided theta is in radians, is equal to A cosine theta plus j A sine theta. All I did in MATLAB though is I just took A, I multiplied it by the exponential, and then I used the MATLAB notation for j is 1j, so it's square root of minus 1, and then I multiplied by the angle. My theta was in degrees, so this is in degrees, not radians, but if I use Euler's formula, the angle has to be in radians. So in order to convert that into radians, I multiplied it by pi and divided by 180 degrees. Okay, does that answer the question?
Yes, thank you.
You're welcome. Okay, so that is an example of a voltage divider with an inductor. So what have I got? I've got a few more examples. I've got 2 more examples. So what I'm going to do, let me just check. I believe, I have another one of my students presenting something at a conference later this morning, and I just want to check. I've forgotten exactly what time he's presenting. So let me just... see if I actually put the time into my calendar. There it is. Yeah, it looks like it's 11 o'clock. So what I'm going to do is I'm going to take a quick break now, and then I'll do the 2 examples, and then we'll have another short break at 11 o'clock. Okay, because I do want to see this presentation my student's giving. I think the presentation is only short, so it shouldn't take more than about 10 minutes. But I haven't put the time in there, so I'll have to check that. Okay. Before we let's have a, like I said, let's have a quick break, and when we come back, I'll do. This circuit is to show how a current divider works with complex impedances, and then we'll do the pièce de résistance and do a mesh analysis using complex impedances. But I'll do that after the break. Any questions? Okay, if not, let's take a 10-minute break, and I will be back after that.
Ooh, excuse me.
Okay, we'll get back to it. Okay, before I continue on, does anybody have any questions about that first voltage divider example? No? Okay, so let's move on, and I'll do a current divider example, right? And again, the way to think about these is to not get too put off by the fact that now we've got different boxes. So maybe just think about it exactly like you do resistances. I'm drawing the European way of drawing resistances rather than the American, or dare I say it, Australian way of drawing resistances. Right? So they're the same problem. It's just again, we've got a few extra steps we've got to do in order to get there. What we need is we need to put this capacitance into an impedance, right? And remember, it's ZC is 1 on J omega C. This time our omega is 1000 radians per second. Right? So our ZC is 1 on J times 1000, and 1 microfarad is 1 by 10 to the minus 6 farads. Okay, so that's 1000. So 10 to the 3 times 10 to the minus 6 is 10 to the minus 3. Inverted is 1000. So it's actually going to be, and I'll go over here, so that's minus J 1000 is what we get for ZC. Okay, so minus J 1000. And the units are ohms. Okay, so then the current divider equation says that I out equals I in times the impedance in the other branch divided by the sum of the impedances. Right? Remember the difference between a voltage divider equation and the current divider equation is, with the voltage divider equation we use the resistance in the numerator of the voltage we're measuring, so of the device we're measuring the voltage, the output voltage across. Whereas with a current divider equation, we flip that, and the numerator value is the resistance in the other branch. Okay, so we use ZR, or the impedance in the other branch in this case. Okay, so that's that. What we didn't do before is we didn't convert I into polar notation, so let's do that now. So it's going to be 400 angle minus 30, and be careful of the units. The units of the current are milliamps, 10 to the minus 3 of an amp. Right, so then we get 400 angle minus 30, and it's degrees. Just be careful you got the right units for your angles, or you know the units for your angles. And then ZR is just 500. It's just the resistance. And then 500, and then minus J 1000. Okay, and then we can fire up MATLAB again and say I out. Well, let's do I in first, and that's going to be 400 times exponential 1J times minus 30 divided by 180 times pi. Okay, so there's our input current. Our output current, therefore, is II times 500 divided by 500 minus J times 1000. Okay, so there's our answer. It's going to be, let me just flip that and move that there so I can still read it. So our answer here is 149.3 plus J 98.56, and the answer is, the units rather, are milliamps. And then I really want to put that in back into time domain, right? So my angle in radians is that. So let's put that into degrees. So the angle is 33.4 degrees. And actually, let's also get the amplitude of the output. So that's the absolute value in MATLAB speak. So it's 178.9 to 4 significant figures. So the output current is 178.9 cosine 1000t plus 33 point, let's do it all to 4 significant figures, and that is in milliamps. Okay, any questions about what I've done there? So what I'm going to do is just over here, I've just pasted all the MATLAB that I used today so far. Right, so you have access to it if you have access to OneNote. Now, can I clear the command window? I can. Okay. So that's an example of using impedances with the current divider equation. So now let's get really funky and do the same thing with mesh analysis. Now I've cheated a little bit here and I've made it a little bit easier for myself, because you'll notice that I haven't given the capacitance in farads or the inductance in henries. I've given a complex impedance immediately. All right, and it depends on the question. Sometimes I do that, sometimes you have to do the conversion, but always check. And a good self-check is for inductors, the impedance is positive, and for capacitors, the impedance is negative. Right? So always self-check that you've got the appropriate sign on your impedance. Right? Capacitors have negative impedances, negative purely imaginary impedances, whereas inductors have positive purely imaginary impedances. Okay, so let's do our thing. I'm just going to erase those two nodes just so I've got plenty of room, and then I think I'll go with the thinner. So now let's have a look. The thing we're trying to find is V out, so let's make both of our mesh currents go into the positive side of V out. So there's I1, and then let's make I2 go in the same direction, into the positive side. So there's I2. And you'll notice we have a freebie, right? We notice immediately, because we only have one mesh current going through a current source, we know immediately what that mesh current is. It's just equal to IS. Okay, so we know the current immediately. We still got to figure out what I1 is, and we do that in our usual way, right? So we write KVL for I1, right? And if we go around that way, it's going to be minus 12 angle 0, right? Because we're going into the negative side here, plus 4 times I1, right? Because we've got a plus and a minus, and we've got a plus and a minus. Okay, and then I1 and I2 are going through C in the same direction, and ZC is minus J4, so that's just going to be minus J4 times I1 plus I2. Okay, that's the first one, and then we also have I1 and I2 flowing through R2, so that's going to be plus 2 times I1 plus I2, and that equals 0. Okay, so now let's move things around. So we have 4I1, we have 2I1, that's 6I1, minus J4 times I1. So it's 6 minus J4 times I1. And then, because we already know I2, I'm not going to write it in just yet, but I'm going to move it over to the other side. So on the other side of the equation, we have 12 angle 0 we take minus 12 angle 0 over to the other side, it's plus 12 angle 0. And then here we have 2 minus J4 times I2, but on the other side that's going to be minus 2 minus J4 times I2. Okay, now I'm just going to write that as, I'm going to use what I know about I2. So it's 12 angle 0 minus 2 times minus J4 times 4 angle 90. Okay, and then rewriting that with just I1 on the one side, I can say that that's 12 angle 0 minus 2 minus J4 times 4 angle 90 divided by 6 minus J4. I think that's right. Please let me know if you think I've got any algebra wrong. You know I do make mistakes sometimes. So that means that I1 is equal to, and I'm just going to put that in brackets, 12, and 12 angle 0 is just 12, so I'm not going to put times exponential J0, just to speed things up. So minus 2 minus J4 times 4 exponential 1J times 90 on 180 times pi, and then divided by 6 minus J4. Okay, so there's our I1. It's well, let's write that down first. Let me just move it over, and then we'll get the polar version of it as well. So that is equal to, and that's 0.1538 minus J times 1.231, and the units for that is amps. But then I want to get that back into polar form. So the absolute value and then the angle back into degrees. Okay, so it's 1.240 minus 82.88. Right, so it's 1.240 angle minus 82.88 degrees. Now, we weren't given omega in this question, right? So I can't rewrite that again in terms of cosine omega t. Well, I could, but I wouldn't have a value for omega, so I'd just have to say 1.24 cosine omega t minus 82.88 degrees. But it's okay to just, in this sort of question, whether you don't have the omega, it's okay just to leave it in polar form. Okay, any questions about that? So I did want to remind you a little bit about, if I can find the, here we go. Now that example in that example didn't have we didn't have to use RF or the matrix equations in order to solve the mesh, but you will come across questions where you have to solve a matrix equation in order to solve it, and the matrix will have complex valued entries. If you have a TI-83 or a TI-84, it won't let you enter complex values into the elements of the matrix. So you can only enter real values. If you have a higher powered one, I think a TI-89 may be able to do it, a TI-99. But if you have an 83 or an 84, you can still do it, but you've got to use this trick, which I think we talked about before. Right, so if you have a matrix like this one here, right, this matrix here, what you've got to do is each element in the matrix has to be replaced by a 2 by 2 matrix, where these two entries are the real component of your complex number. This entry is the imaginary component of your complex number, and this one is the negative of your imaginary component of your complex number. So for this example, the 2 by 2 complex valued matrix will end up being a 4 by 4 real valued matrix. And you can still solve it. And let's just have a look at doing that. So let's just grab that and let's see if we can, right? So how do we want to do this? So let's do this. What I'm going to do is I'm going to do the complex matrix first, right? Right, so there's our first one, 5 minus J6, 7 plus J8. Okay, so there's our complex matrix, and let's just add another 1 and a, let's just add a 1 and a 1, so we get an RF style matrix, right? And then I believe MATLAB will let you do a complex style RF. So that's the way to do it if your computing engine can cope with complex valued entries in matrices. But all is not lost. We can do the same thing, but we need to do it in a slightly different way, right? So here what we can do is we can do, right, there's our 2 by 2 replacement for 1 plus J2. There's our 2 by 2 replacement for 3 plus J4. and there's our 2x2 replacement for our 1 in the example. And then I should be able to do, so my 2x2 replacement for so 5, and then plus 6 because it's already negated. There's my 2x2 replacement for 5 minus J6. There's my 2x2 replacement for 7 plus J8, and again I need my 2x2 replacement for 1. Okay, so there's the real matrix equivalent. Just check that I got all the, I think that looks right. And then I can plug that into RF. And what we should see is there's our 414 and minus 0.0414 and minus 1.006. Right, that looks good. And then 0.1302 and minus 0.1124. 0.1302 and minus 0.1124. Okay, so that should also be doable. And again, I'm going to copy that into today's lecture notes. Actually, the topic 10 lecture notes. So we've got all the stuff in the one place. I'm sure I used to have a CET materials, but I don't have it anymore. That's a little annoying. I wonder why I deleted it. So what I thought we might do is
I still see the materials chat.
oh, you do? Okay.
Yeah,
Wonder why.
I'm not sure. I'm not sure.
Oh, I see. I've just got it closed up. For some reason it's... There it is. Okay. Yeah, there we go. Yeah, it's funny. It doesn't close up the discussion one. Okay, thank you. So, let me just... So I've got another tutorial sheet, and let me just open that up here. And let's have a look at the tutorial questions. Okay, so I thought it might be good to have a go at just converting from capacitance and inductance into impedances. And I'm doing a little bit of sleight of hand here, right? Because I've been talking about omega as being in radians per second. But now on this tutorial sheet, I've changed the frequency unit to being in hertz. Because usually when you talk about frequencies, you talk about the frequencies in hertz or megahertz or kilohertz. right? So just remember that the frequency we need is in radians per second. And the way to get from hertz to radians per second is omega equals 2 pi f, where f is in hertz. Another way to think about hertz is as cycles per second. Sometimes it used to be written CPS, cycles per second. So, and you can if you think about a sine wave, right? One cycle of a sine wave happens over 2 pi radians. So that's why you multiply f in cycles per second by 2 pi in order to get into radians per second, because there are 2 pi radians in one cycle. So because my bingo and in fact my breakout room, I should have noticed that earlier, but I didn't. Looks like my bot isn't there. Yeah, it's there, but it's offline. So what I'm going to suggest is yeah, let's why don't we all might be a bit much. Yeah, why don't we all try the first question, right? So I'll give you maybe 3 minutes and try and figure out what question 1 is, what the ZC for question 1 is. And remember that ZC is 1 on J omega C. So we'll try each of those. I'll give everybody, say, 3 minutes. And we'll try. I'll go through the answers. I'll go through all of them, but let's have a go at figuring out what that one is, and then we'll go through that and the subsequent ones. But have a go of as many of them as you can while I give you the 3 minutes. Okay. So let's just look at it. So 500 hertz. Let's see who we got. Mehul Kumar, what do you get for omega for 500 hertz? No answer?
Professor, maybe it's minus J 31415.9.
So you're giving me the final answer 1415, and that's in ohms. Okay, so the omega is just 2 pi times that, so that's going to be 1000 pi radians per second, and then it's 10 farads. So, hold it. Yeah, so that's going to be, sorry, I misunderstood. So that's our, as you say, it's going to be 3141.5. I think, is that right?
I got like 31415.9.
31415.9. So 500 hertz, that's just going to be 1000 pi, right? So it's going to be the omega is going to be 3141.5 radians per second. And then, so if we take that over here, and that's going to be 1 on J times 3141.5 times C, and now C is 10, right? And then we've got to do the 1 on J, so that's I can't do that in my head, so let's just fire up MATLAB. And see what we get. So it's going to be 1 on J omega, which is 2 times pi times 500, and then times C, right? So it's going to be, what's that? Minus 3.18 by 10 to the minus 5. Right, so it's a very small impedance. Okay, I apologize, I didn't realize this was going to happen. What I'd suggest is we take another 15-minute break, or while you do these, or have a break. When we come back, I'll work through the rest of these, and we can get the answers. But I do want to see this presentation from my student. Okay. I apologise for that. I didn't realise it was going to be. So we'll make it a 15-minute break, just so that I can hopefully see the whole presentation. Okay, thank you. I'll be right back.
Jackie, do you expect to do any breakout rooms or anything in this session?
No, I don't think so.
Okay, very good.
We are a bit large. Let me see.
I do see your screen.
Okay, you don't need to record now until we start. It's fine.
Right, I'll just wait till you tell me for when to record.
Yeah. I just want to share the agenda and just make sure that everybody's here. Yeah, I hope everybody's here because some of them. Let me see. So we don't have 10 attendants. I think we should have about.
Yeah, we do have 10.
Yeah. Okay. Okay. Then it's 11:05 and then we start. It's fine.
Okay. Hang on 1 second, I have a cable problem here.
It's fine. Because the first speaker is not here, so he just withdraw. He's just withdraw his presentation.
Okay.
So then maybe you could start. We start on time.
Okay, here goes.
Okay. Hello. Good morning, everyone. So welcome to the poster section, track 3, research posters, and so the time should be 11:05 and to 12:20. So here is the list of the posters. And unfortunately, the first speaker just emailed me last night, and he said he can't come today. So therefore we still have 4 minutes, and I will say I will just keep. If somebody cannot make presentation, we just hold and wait because I want to keep the poster on the schedule, right? Because for example, other people they may come and just expect to watch the poster on schedule. So therefore, we still have 4 minutes to go. So here is some. Today we have 14 posters, so that's a lot. Right? So here is some rules I want to share with you. So each of you going to have 5 minutes totally for your presentation, right? And then so you have 3 minutes to talk. And I will remind you, and when you have 30 seconds left, okay? So when you have 30 seconds left, I just, hey, excuse me, you have 30 seconds left, and then please wrap up your poster presentation within 30 seconds. I know it's challenging, all right? I know it's challenging to make presentation in 5 minutes, right? To finish in 3 minutes, right? But again, we have a lot of submission this year for the poster presentation. So therefore, this is the way we can get everyone involved and make presentation. Okay, and in addition, I email you about your poster slides because you only have 3 to 5 minutes and to present or answer the question for poster, and we would like to get your poster slides and then share with the audience later, and because they may not have enough time to digest your presentation within 5 minutes, right? So therefore, I share a Google Drive folder. So if you go to the chat, and you will see the Google. Let me see. So if you go to the chat here, so you can see the Google Drive link. So please after the presentation, please upload your poster into this folder, and you just need to log in. Using your Google account and then to upload your poster. So when you upload your poster, please put a name like this in the format. Right? Here is track 3, and then the title of your poster. Again, I hope you could share your poster. I really appreciate you, and if you do that, okay. So we have 2 minutes to go. I will say maybe the first speaker going to set up to set up the presentation. So the first speaker is Kvl, right? You are here, right? Great. Okay. So let me stop sharing, and then you set up yours. Okay. Good.
Sounds good. Thank. Okay, I'm ready. So should we just wait until 11:10?
Yeah, because we want to try to get schedule.
Okay.
Yeah. Okay, maybe. Yeah. Okay. So our first speaker is Kvl, right? And from Fairfield University. Yeah. Please go ahead.
Hi. So we're a group of 4 people from Fairfield University. I'm going to be presenting today. I'm Guillem Perez. Then there's Phil Ruggiero, Joe Scannell, and Jack Shishati. And we have 2 faculty members, Dr. Peter Kutsukus and Dr. Tom Littleton from the FAA. And our presentation today is named Securing Information Contained in Boarding Pass Barcodes. A little bit of background information from our project. Boarding passes are very common in the air travel industry. If anybody has ever been to an airport, whenever you go check in, they will give you a piece of paper with a barcode in there, and it contains some information that the airline needs to know. They have become a little bit more advanced as time progresses, and now we have mobile boarding passes that you can just pull up on your phone. And so the information that's contained in those barcodes is encoded, and it is made easy to read for a barcode scanner, for example, at the gate or at TSA. And the most commonly used in the industry are 2D barcodes, and specifically Pdf417 barcodes. So this is an image of a regular boarding pass. In this case, we see there's 2 kinds of barcodes. One of them is just used for airline purposes, which is the regular barcode that we could see at a product at a store. But then at the bottom, we see a Pdf417 barcode, which is the one that contains all the relevant information from the flight and from the person who is taking that flight. So in here, we have 2 examples of 2 barcodes that we generated in this case with this string as a test. And so that's how information is encoded in those barcodes. So there's usually last name, first name, then reservation number, origin, destination, flight number, and so on and so forth. And so the purpose of our project was to make them more secure. And so in the left corner, you can see a encrypted barcode, which the information is encrypted, and then it's just converted into a barcode using AES-256. And then on the right, we can see a not encrypted typical boarding pass, and they have the same information. Just one of them is encrypted. But size doesn't really matter because size can be controlled via different parameters when you're creating a barcode. So how are we doing this? We are using a Python script to generate those barcodes with the encrypted information in it. And the information is going to be fully encrypted using AES-256, which is federally...
Excuse me, Guillem.
Yes.
30 seconds. Yeah, your second left. Right?
Okay, so it's used using AES-256, which is federally recognized, and in order to read it, we have an app that will read the barcode, and this is how it looks like. We have the generator, the database, and the reader, and then the results. We have proven that it's possible to encrypt it, and we are compromising a little bit on availability because the information is not readily available, but it's more confidential, so that's kind of a success. And so one of the possible solutions for the future would be 2-factor authentication, which could be time for another discussion. And we have seen that it's an efficient way to make it more secure. And lastly, we want to thank Dr. Peter Kutsukus and Dr. Tom Littleton for their continued support and their ideas to keep this project moving forward.
Yes, thanks for the talk. Any question from the audience? Okay, I have one quick question. Very nice work. So should we need to change the standard of the passcode because of your new technology?
Yes, we think that we should change the standard, because right now the information is readily available, and anybody with a barcode scanner on their phone and any app can read that information, and so it leads to you could infer a lot of information from just looking at a barcode. So if somebody posts a picture on Instagram or on any social media, you could guess a lot of private information that you shouldn't be able to access. So that's why we think that we should add encryption to it, so that just the airline and TSA, for example, could have access to that information.
Very nice. Yeah, let's just speak. So can I stop sharing, and then I could show the next
Is that everybody coming back? Everybody back? Yeah, okay. So the next question, the only difference between questions 1 and 2 is the 600 hertz, right? So
I can't see you.
You can't see me? Oh, did I? I didn't share my screen. What happened to my screen? Why did my screen go away? That's no good. Sorry, I'm going to have to rejig the screens. Why did my screen stop screaming? That's no good. And where are we? I need to go back there. I didn't... Oh, it probably didn't like me going... Okay, sorry about that. And let me just get my screen set up so I can see side by side. There we go. Sorry about that. So yeah, the only difference, you can see my screen now, yeah?
Yes.
Yeah, okay, thank you. So the only difference between questions 1 and 2 is that now we have 600 Hertz rather than 500 Hertz. So that means we've got 12, let me write that properly, 1200 pi radians per second, which I don't know how to figure that out in my head. Sorry. So let's just plug it into MATLAB. So it's 1200 pi. So it's 3770 to 4 significant figures. Right, so that's 3770 radians per second to 4 significant figures. So then in our ZC, and it's right, so our ZC for this is ZC1, ZC2 is going to be 1 on J omega C, 1 on J times 3770, again times 10. And again, let's plug that into, right, so it's going to be 1 on J times omega times C. So it's 2.653 minus J 2.653 by 10 to the minus 5. And again, our units are ohms. Okay, so that's one thing it's kind of interesting about capacitors and inductors. As the frequency changes, the impedance changes. So it's one reason why we have to be sure we're operating at a single frequency, because if we're not operating at a single frequency, the impedance changes. You'll also notice that the numbers are quite different in range compared with the resistors, right? Resistors, for simple problems, we use 2, 4, 8, 10, etc. But for the other ones, we used sorry, I just forgot. For the other ones, we used lost my train of thought. For normal resistances, for the small ones, we use 2, 4, 8, 10, 12. And then for more reasonable resistances, we used 1K, 2K, 10K, 18K. Here we've got much smaller impedances for this example. But what you'll find is there's a much larger range of both capacitance and inductance and impedances. It's not unusual to have a 10 millihenry or a 10 microhenry inductor. It's not unusual to have a 1 picofarad capacitor or a 10 millifarad capacitor. But the multipliers tend to be much smaller for capacitance and inductance than they are for resistance. Okay, does anybody have any answers for any of the rest of these? Dylan, do you have any answers for question 3?
No, sorry, I wasn't working through.
That's okay. So, that's where breakout rooms are useful. Sorry, I should have got my computer better set up. So, well, let me just. So, if you want to work through them, and I'll try and go through them more slowly. So the nice thing is these next 2 questions, we're just using the same frequencies, but now for question 3 and 4, we've got a 10 Henry inductor. Let me make something clear. Having a 10 farad capacitor, that's a big capacitor. Normally they're in the order of millihenries or millifarads or microfarads. Having a 10 Henry inductor is also a pretty big inductor. Again, they're normally millihenries or microhenries, right? They're normally much smaller. So for question 3, so let's go for ZL3, and remember the impedance for an inductor is J omega L, and let's call it L3. All right, so in this case our omega is 314, right? So J times 314 1.5, and then times 10, right? So for our impedance for question 3, or number 3 in question 1, it's going to be J 31,415 ohms. Okay, and then ZL4 is just J times the different omega value, and again times 10, so that's going to be J 37,700. And then ohms. I'll just scroll that up a bit so you can see it. There we go. Okay, and now the next ones, questions 5, 6, and 7, are at a completely different frequency, right? So if you listen to FM radio, then you know the frequency of FM radio is somewhere usually between about 88 megahertz and up around 110 megahertz, that sort of range. AM radio tends to be a lot lower in frequency, about 600 kilohertz to about maybe a megahertz, maybe just a bit over a megahertz, 1200 kilohertz. Right, so 5 is a capacitor again. So ZC5 is again 1 on J omega C. That's C5. But this time we've got omega is 10 to the 6 hertz. So we need to multiply that by 2 pi to get it into radians per second. So it's 6.28 by 10 to the 6 radians per second. But this time the capacitance is small, so it's 10 by 10 to the minus 6. And we can sort of cross those two out. So it's 1 on J 20 pi, which I can't do that in my head either, so let's fire up MATLAB. 1 on 1J times 20 times pi is minus J 0.0159, and let's just make it minus 0.01592. So let's just write it out. A 0.01592 ohms. Okay. So yeah, that was question 5. Any questions about that? Okay, question 6, ZL6, and again it's an inductor this time, so it's J omega L, and J again, omega again is 2 pi by 10 to the 6th, and L is 10 by 10 to the minus 3. Right, so that's going to be, well, we can sort of, so that's by 10 to the 4. So what's that? That's 6.28 by 10 to the 4, which is 62,820-ish. J ohms. Right, let me just check that I got that right. So 2 times pi by 10 to the 6 by 10 millihenries, 10 by 10 to the minus 3. Right, so it's, yeah, 62,000, well, it should be a 3 in that 4th significant figure. Okay, 62,830 ohms. J, 62,830 ohms. So part 7 is a little different. So now we have an inductor in parallel with a capacitor. So let's have a look at what that looks like. Right, so there's our ZL and there's our ZC, and Z equivalent, which is the overall impedance, is just exactly what you would expect, right? These are 2 in parallel, so it's going to be 1 on ZL plus 1 on ZC, just like as if they were resistances, but now our impedances, we're using impedances instead, right? And then, so what do we get? We're still, it's basically the answers for questions 5 and 6. So we need to use ZC5 and ZL2, so minus J 0.0152. Well, the 68,000, I forgot the number again, 62,830. Sorry, I wish I had a better memory. 62,830 J plus 1 on, and this is minus J 0.1592. What does that look like in MATLAB? So it's going to be 1 on, 1 on, that number, plus 1 on, that number. Okay, and because it's the capacitance impedance is so small, that's the thing that's going to dominate. Relative to the impedance of the inductor, and in fact it makes a slight difference in the fourth significant figure, but really it's just the thing that's going to dominate is the impedance of the capacitor because it's so small. So there's going to, even to the same number of I didn't get the right number. I should have put another 0 in there. So minus j is 0.01592. It was 15915 in MATLAB, but it's still effectively the same. And again, the units are ohms. Okay? So that's that. I do have some other questions here, but I'm going to leave doing those until next week when you've had a bit more of a chance to digest what we've had. What I would like to do now is go back to this slide and talk about some of the homework. Before we go there, does anybody have any questions about what we've done so far on capacitance, inductance, reactance, and impedance? That's basically and we got a question there somewhere. There we go. Why is the answer for the right? So the ZCs should always be negative. Did I not make it negative? Yeah, ZC is negative there, and I think we got a negative ZC there, right? So it, the reason it's negative, right, is because 1 over J is equal to J on J squared, which is equal to J on minus 1, which is equal to minus J, right? And because our ZC equals 1 on J omega C, you always get a negative. Okay, so I suggest we start with homework 6, and let me just fire up web work and let's have a look at that. So I've forgotten which one was homework 6. assessment, there we go. Homework 6 was Thevenin and Norton. So let's have a look at Thevenin and Norton. So problem 1. Looks like I've actually done this one. So this homework 6, did we have a previous one? Let's just add a new page for homework 6, Thevenin and Norton. And hopefully I can put that picture in there. There we go. Okay, so remember what, let's just remember what the question's asking. So find the equivalent circuit for the schematic shown around R3. R3 is the load using Thevenin's theorem. Enter the values for the equivalent circuit below. So don't worry too much about the numbers just yet. So let's think about what happens. The first thing I suggest you do in any of these Thevenin and Norton equivalent circuits is to remove the load, because that tends to make things a little simpler, right? So if I remove the load, which is R3, what I end up with is effectively two distinct circuits, right? I end up with a circuit involving a voltage source, right, Vs, and that's R1, and that's R2, and a circuit involving a current source. And the question's asking, well, the question's asking what is VTH and what is RTH, right? The Thevenin equivalent voltage and the Thevenin equivalent resistance. So to get the Thevenin equivalent voltage, we need the open circuit voltage. So this circuit here that I've just drawn will allow us to figure out the open circuit voltage. And the open circuit voltage is measured between here and here. And let's just call this node L and this node R, right? And in this particular case, VOC is equal to VR minus VL. So now the question is, what is VL, what is VR? Well, VL should be easy, right? We just did a voltage divider question. So it's going to be R2 on R1 plus R2 times Vs. And in some ways, VR is even easier, because all we've got is a current source flowing into a resistor, right? So there's VR. And now we can say that VOC equals ISR4 minus R2 on R1 plus R2 times Vs. Excuse me for... Sorry, I'm going to have to close down OneNote. It started playing silliness with me again. Right, as I said, let's go back to green, thin, right? So VL is equal to R2 on R1 plus R2 times VS, and VR is equal to IS R4. We can just substitute both of those in to get VOC. Okay, that's how to get VTH. So the question now is, how do we get RTH? Well, for this particular question, we can just use the simple approach, right? The equivalent resistance approach. So the equivalent resistance approach, if you recall, says that you take the circuit, you remove the load, you replace, you can only use the equivalent resistance approach if there are no dependent sources, and there are no dependent sources in here. We've only got an independent voltage supply and an independent current supply, right? So then we can say we replace each of those with their ideals, and in the case of the voltage source, it's a wire. In the case of the current source, it's an open circuit. So if we do that, see if I can, all right, we end up with R1 and R2 in parallel, right? And then we don't have R3, and we're just left with R4 over here because we replace IS with an open circuit. Okay, so that means that R equivalent, the equivalent resistance as measured through where the load resistor was, is going to be R4 plus R1 in parallel with R2. Okay, so that's question 1. Let's have a look at question 2. Okay, question 2 is a little trickier. Question 2 looks like RL is here. Let's just check. Yeah, RL is the load. So let's copy that image and let's paste it back here. And we need to find the output voltage. So this is question 2. So this one's a little trickier because we've got a dependent source. So we can't use the equivalent resistance algorithm for finding the Thevenin resistance. Okay, so that's good. But the first thing we do in all of these, as I've said earlier, is we remove the load. So there's our circuit. And again, the things we want to find are VTH and RTH. And for VTH, we pretty much always need to find the open circuit voltage. RTH, we have a little bit of leeway. We've got to 3 algorithms we can use to find RTH, but for the open circuit, for the Thevenin voltage, we pretty much need to use the open circuit voltage approach. Okay, so the open circuit voltage approach, let's just go back and see what the dependency was. It's Vx is on R1, so it's 0.25 times Vx is my V2. So this is, let's just call it K times Vx. Okay, so if we're measuring our VOC here, that makes it, right, so we're going to go, the voltage here, let's call that A. So the open circuit voltage is going to be VA minus V2, right? Because we're dropping in voltage when we go from VA. And VA is nothing more than R2, we've got a voltage divider, divided by R1 plus R2 times V1 minus V2. Now we might have to figure out what V2 is, or actually it's, V2. So V2 is K times Vx, and Vx in this instance is nothing more than R1 on R1 plus R2 times V1. Right, so the overall expression should look something like that. And again, let me scroll up so you can read it. Jonathan, does that cover enough about what you wanted in question 2?
Yep. Yeah, nice.
Okay. Very good. So I can use numbers here, but you've all probably got different numbers in your questions, so I don't think it'll help anybody in particular, so that's why I'm making it more generic. Sorry, let's go back to web work and go to the next problem maybe. Okay, that's a pretty straightforward one, sort of. So let's have a look at that one. Yep.
Just to clarify, that K value was just whatever the value of V2 was, whatever that number was in front of Vx?
Yeah, exactly.
Is that what that?
Yeah.
Okay. All right. I just want to make sure.
Yeah, you're going to get, so in my case, the K value was 0.25. Right, but I don't think everybody gets the same K value, so I didn't want to put 0.25 in there and confuse everybody. Maybe I confused everybody by using K, but at least you won't use my 0.25 value if yours has a different number there. Okay?
Yep, just wanted to make sure. Thank you.
To find RTH for second problem is the same how defining question 1.
Oh, okay, sorry. So you want to, okay, let's have a look at, I didn't do that. Let me go back and do that. So, okay, so we've found VOC. So you're right, I didn't find RTH. So how do I find RTH? Well, I have a dependent source now, so I can't use the equivalent resistance approach. However, I do have at least one independent source, So I can fall back on the open circuit current, open circuit voltage, short circuit current approach, right? I've already found, I have to find VOC. I nearly always have to find VOC. So the other thing I probably need to do to find RTH, and it's gone again. Let's just see if I can, yeah, it's gone again. Let me just kill one node again and try again. I'm wondering if there's something I'm clicking that does that. It's really annoying. Okay, so we basically take the same circuit, right? But now we connect a wire here and we want to find out what ISC is. So we need to do something probably a little bit more funky. So again, I would probably go with mesh analysis, because mesh analysis gives us currents and we're after ISC. Right, so what we can do here is the I1 Kvl equation is minus V1 plus I1 R1, right, because we're going into that side, plus I1 minus ISC times R2, and that whole thing equals 0. And then the ISC KVL, let's just use the right color. The ISC KVL is ISC minus I1 times R2, again because we're going that way, plus V2, which is KVX, and that equals 0. Okay, and then we should end up with a, what is it going to be? It's going to be R1 plus R2 as the coefficient of I1, minus R2 as the coefficient of ISC, and plus V1 okay, and then here we've got R2, so we've got a minus R2 as the coefficient of I1, and a plus R2 as the coefficient of ISC, and then KVX is going to be K times R1, oops, now it's not, we can't use that, we have to look at Vx is I1R1, right, so I should have put I1R1 in here. Right, so K times I1R1, so that means instead of just minus R2, I have a K1R1 as well, or KR1. Let's write that a bit more neatly. Okay, and then I don't have anything on the other side. So my RF equation without any numbers would look like that. Okay, so that and then you would solve that for I1 and ISC, and particularly we're interested in ISC. Right, that'll give us I1 and ISC, and then we can find RTH is just equal to VOC, which we got up here, divided by ISC, the short circuit current. Open circuit voltage divided by the short circuit current gives us the Thevenin resistance. Okay?
BOC divided by what?
By IS. Oh, sorry. Ah, it stopped again. So the open circuit voltage divided by the short circuit current. ISC. Right? You should know this. This is stuff we've done, right? So the that RF, solving that RF gives us I1 and ISC, and then RTH is just VOC. Let me scroll up a bit so you can see it, divided by ISC, right? Where we've got VOC already, and we've just solved for ISC. Okay, that was problem 2. Let's have a look at problem 3. And still on Thevenin. Okay. So this one is these questions gradually ramp up, right? Remember, we've got 3 ways to find RTH. We've got the equivalent resistance method, which we could use in the first question. We've got the open circuit voltage short circuit current technique, which we could use if there is one independent source. And then the third algorithm that we've got to use, or that we've got in our armory, is the applier voltage technique, right? And the applier voltage technique can be used on any circuit. It doesn't have any constraints. This circuit has 2 dependent sources and 0 independent sources, so we can't use equivalent resistance, and we can't use the open circuit voltage short circuit current approach. So we have to use applier voltage. So let's use applier voltage. How do we do that? Well, we basically just do as the name suggests. All right, and we apply that voltage, and that's, I don't know, 10 volts, 42 volts, 100 volts. Right, we just use that. So then we define some meshes, maybe. Right, we go I1, and we go I2, and we go I3. In fact, let's draw I3 the other way around so that it's coming out of the positive side of the active source. Right? So the number we're after, this applied voltage is V nu, and what we're after is I3 or I nu. In fact, let me relabel I3 as I new. Maybe? Here we go. Okay, so I1's easy. I1 equals IS, and let's see what the dependency is. IS is K times IX. Right, so that's going to be I1 is K times IX, and it's kind of interesting, and we know that IX is equal to I1 minus I2. Okay, so we can rewrite that as K times I1 minus I2. And what does that tell us? That tells us that 1 minus K times I1 equals minus K I2, or that I1 equals minus K on 1 minus K times I2. So then let's look at the middle mesh and I2 mesh. Tells us that, what does it tell us? It says that I2, and again let's just get our polarities right, I2 minus I1 times R1, right, minus VS plus R2 times I2 plus I new, and that equals 0. And let's just see what the dependency for VS is. VS is, let's call it, I don't know, KM, maybe M, is M times IX. And we know IX is I1 minus I2. Okay, so let's just rewrite it out again. So it's I2 minus I1 times R1 minus M times I1 minus I2 plus R2 times I2 plus I new equals 0. Maybe we can rearrange that. So we've got a minus R1 minus M times I1. We've got an R1 plus M plus R2 times I2. And we've got a plus R2 times I new, and that equals 0. And then for the I new mesh, right, we've got R2 times I new plus I2 minus V new equals 0. And I said V new is 10 volts maybe, I don't know. So that's just R2 I2 plus R2 I new equals 10. And now let's see if we can put all of that together. I don't know whether I want to use this. I think I might just rearrange this and say that it's I1 plus K on 1 minus K I2 equals 0. And then just do a 3 by 4 RF matrix. Right, so that's going to be 1 K on 1 minus K, 0 for the I new coefficient, 0, and it's going to be minus R1 minus M, R1 plus M plus R2 for here, and then R2, and that equals 0. And then here we don't have any R1s, I1s rather. We've got an R2, we've got an R2, and we've got a 10. And if we solve that, we'll get our I1, I2, and I new. The one we're really interested in is I new, because once we've got that, we can say that RTH equals V new, which is 10, divided by I new. So that finds us RTH for question 3. I wish it had stopped doing that. Let me just take a screenshot of that. I'm not going to write that out all again. Let me just insert the screen.
M was?
Sorry, what's that?
Can you explain again what M was? You kind of lost me there.
Again, it's because I have, in this example, I have two dependent sources, and each dependent source is let's just make that a bit bigger. Each dependent source is proportional to some other measurement, right? So here's, right? So here's IS, it's a dependent current supply, and it is K times IX in value. My K is 24. And VS is also a dependent source, this time a voltage source. And rather than use K again, because they're not equal, I used another variable called M. Maybe I should have used something else, S, T, something. But it's just the 24 is K for me, and for me, M is 450. But your numbers are probably different. That's why I'm not using my numbers, just so I don't confuse you on that score. Obviously, I've confused you on the other score of...
No, it's fine. I understand now.
Okay, so...
I didn't see that first part.
Yeah, that's okay. So there's the definition of M there. And then I don't think I wrote down... Yeah, I just wrote down there. There's the K for IS. Okay? Okay, so I'm not going to go through finding the open circuit voltage, because we still need to find VTH, right? We haven't, we only found, where we got to, we only found RTH from that. But what we need to do is we need to find VOC to find the Thevenin voltage. And there we remove V nu. And that's the thing with Thevenin and Norton problems, particularly when you're using the well, actually, when you're using this approach, or when you're using the open circuit voltage short circuit current technique, usually you've got to solve two mesh problems. You've got to solve this problem where you've got, in this case, when we're using the applier voltage technique, you've got to solve the problem with V nu in place. And then if you want, after the open, if you're doing a Thevenin problem, you want to solve the same problem but with V nu removed, because you're interested in VOC, which is the voltage across R2 when there's no load or V nu connected, right? If it's if instead you weren't after the Thevenin voltage, the open circuit voltage, you're after the Norton current, you would replace V nu in this diagram with a short circuit, and you'd be interested in the current through that short circuit, because the current in that short circuit is the Norton current. Okay, so that's problem 3. I'll just have a quick look at some of these other ones. Right, so here's a Norton problem, right? We're after the Norton current, and again the Norton resistance, which is going to be the same as the Thevenin resistance. And let's just grab that picture and pull it over here. So what do we want to do with this one? So again, we've got we've got two independent sources. So because we have two independent sources, I recommend using the equivalent resistance technique, right? Remember the equivalent resistance technique, we take the circuit and we replace VS with its ideal, which is a short circuit. We replace IS with its ideal, which is an open circuit. And then we just look at the equivalent resistance to find RTH, right? So there's R1, there's R2, there's R3, and there's R4. So what is this? This is, so this piece here is R1 in parallel with R2, and that's in series with R3, and that whole thing is in parallel with R4. So RTH is equal to R4 in parallel with R3 plus R1 in parallel with R2. Okay, that gives you what RTH is. And then it's a matter of finding the short circuit current. The easiest way probably to find the short circuit current is to just put a short between A and B and solve the circuit. Right, it might be a little difficult because you've got 4 meshes. But actually no, you don't. You don't, do you? Because if you put a short circuit across A and B, then R4 is shorted out. So R4 has takes no part in the equation, right? So we're just left with, to find the short circuit current, that's a bit wonky, isn't it? Oh well. Right, so we've just got to solve those 3 mesh problems. We do have a problem because it's a super mesh, because we've got both the green mesh current and the red mesh current flowing through IS. Right, so we probably want to do something about that. Just use the super mesh approach. Eek. Don't know what I did then. Ah. Let's try that again. Wow, baby. Let's just draw that in the right colors. Don't know why it changed colors like that. That's just bizarre. Again, I probably hit some hotkey, but I have no idea what it was. Okay, so there's our R1, R2, our R4 is shorted out. And then we want an I1, maybe an I2 up here. The one we're really interested in is this one, which is ISC. Okay, so we want to solve for ISC to get our Norton current, because this is a Norton question. Okay, let's have a look at problem 5. And again, this is a ramping up of the problems, because now we have a dependent source. We have an independent source as well, V2, but we have a dependent source, so we can't use the equivalent resistance approach in order to solve this one. Right, so what do we want to do? Probably open circuit voltage, short circuit current technique. Right, so remember what we do is we first of all remove the load. So we remove the load. Yeah, sorry, my tablet has gone wonky. There we go. So remove the load. And what we want to measure is VOC, which is actually VTH, but we're interested in VOC this time to get the Norton current and the Norton resistance. That's R1, that's R2, that's V2, that one was V1, that's R3. Right, and because this is open circuit voltage, VTH, this resistor here doesn't take any part, so the voltage at this node here is also VOC because there's no current flowing out. But again, we're going to have to probably do a mesh analysis. We could do a nodal analysis too, right? In fact, why don't we do that? Let's do a nodal analysis. Right, we can say that the nodes we're interested in are here, A, B, and C. And the thing we're interested in is VOC, which is VC. It might be a bit dark. Let's try a different color. That one might be a bit better. Right, so A, B, and C. We already know that VA is equal to V1. Right, and let's just see what the dependency was for V1. V1 is 2000 I naught. Which is 2000 I2. Right, because I2 is the one flowing through R3, which is the red one. Let's just label it as I2. Let's label the green one as I1. Okay, so there's the thing we know we have a freebie with node A because we have a voltage source connected between the reference and the node. And then node B, we're going to have to do actually let's do it's not gonna let me undo. No, it's not gonna let me undo, so I'm gonna have to
that 2000 should be like a K value as well, right? Isn't it?
You're right.
That 2000.
You're right. I should be consistent, shouldn't I? Sorry about that. Let me just yeah. So that should be a K. Yeah. So that should be a K. Right. Now what was I doing? I wanted to do nodal analysis. So we've got our now we've got a super node here, right? So that's a super node. And we've got I naught. So I want my element R2 current to flow in the same direction as I naught. Let's just make I3 go that way, and we don't have any current there, so we're all good. So the super node, we get IR1 minus IR2 minus IR3 is 0. Okay, and IR, let's just do each of the individual ones. IR1 is VA minus VB on R1. IR2 is VB on R2. And IR3 is VC on R3. And then we can substitute all of those into here to get an equation in and I probably, now that I think about it, I probably don't want to use the mesh for this. I need to use my KIR2, right? So I can use this version in here as well. And then the other piece I need from my super node is I need to use the Kvl equation, right? Which is VC minus VB equals V2. And that should give us right, so we know what VA is, so we can substitute that into here. So we're just left with an equation in VB and VC here and another equation in VB and VC here. Let's just write this one out in full. So it's IR1, which is K IR2, right, VA, minus VB.
Sorry to interrupt there. For VA, couldn't it be K times the current through R3? Because that is where
you are correct. Thank you. Very well done. Right, so you're right. So that's where the I out is coming through, and let's just check that that's what we're looking at. Yeah, we're interested in I out, so you're right. Sorry about that. Well called. Okay, so that's KIR3 minus VB divided by R1 and now I probably want to I probably should have done, that's K times VC on R3, right? So let me just substitute that in there. So K times VC on R3 minus VB minus IR2, which is VB on R2, minus IR3, which is VC on R3, and that equals 0. Okay, so then that probably is enough. We have two equations in two unknowns. Right, the first equation we have is this one, so that's minus 1, 1 V2, and we've got a 0 here, and the VB coefficient is minus 1 on R1 minus 1 on R2. And the VC coefficient is a little funky. It's minus 1 on R3. And then plus K on R1, R3. And if we solve that, that'll get us VB. Something is chewing up the CPU on my machine for some reason. So that'll give us VP on VC. And the one we're interested in, what's the one we're interested in? The one we're interested in is VC, because VC equals VOC. Okay, that'll get us that one. Then we have to solve the same circuit, but this time with a short circuit, and we want to find ISC. And this time I'd probably solve it using mesh analysis, because the thing I'm trying to find is a current, and mesh analysis finds currents. Okay, so like I said earlier, you usually have to solve two either mesh analysis questions or two nodal analysis questions, or one, in this example I would have had to solve one nodal analysis question to get VOC and one mesh analysis question to get ISC, the short circuit current. I'm going to wrap up soon, but let's just have a quick look at question 6. Okay, question 6 is, it's okay. So, do you remember what source conversions are? Anybody? Well, remember, source conversions are these things, right? We can have a Thevenin equivalent, right, which has VTH and RTH, and we can convert that into a Norton circuit directly. Okay, so for this example, right, we could replace VS and R1 with a current source and a parallel R1. Okay, that might make the problem a little easier. Okay, because then we've just got two current sources and R1 in parallel with R2, which we could probably find out, replace it with its single equivalent resistance, and then that R1 in parallel with R2 is in parallel with R3 plus R4, so we could probably find the overall equivalent resistance pretty easily. In fact, this particular question, once we've done those source conversion, we can probably solve this question. In fact, we could solve it anyway using the simpler method, the equivalent resistance method, at least finding RTH or RN. Remember, they're the same. Okay. So I did have another question about I don't know, did I have another question about problem 2 of superposition? So let's have a look at superposition. Okay, Giovanni, did you have a particular question about problem 2? So superposition, we've got two independent sources. Part 2. Okay, so the first part should be pretty straightforward. Let's just, yeah, I got that one right. So then the sub-problems. So what are the sub-problems? Let's just take a copy of that image and go over here. And I won't put it there, I'll put it into a superposition homework. Okay, so the first one, I'm going to keep the current source and that makes the circuit that I want to analyze this one, right? So that's R1, R2, R3 and R4. So this circuit's, and what we're after is I out, right? So this is just a current divider, right? We don't have to do anything fancy with this one. The tricky part with this is that it's got 3 branches. So really you want to convert that into the branch you're interested in and then lump everything else together into an equivalent resistance. And in fact, I'm going to lump R3 and R4 because that's just R3 plus R4. And then our REQ is just R1 in parallel with R2, right? So then our I out 1 is just going to be equal to the current divider equation, which is the resistance in the other branch, REQ, divided by the resistance in the other branch plus the resistance in this branch, times the input current, IS. I should have called that IS. Okay, so that should give you I out 1. And then I out 2, we replace IS with its equivalent, which is an open circuit. So we're just left with R1. And then our voltage source here so that's R1, that's R2, that's R3, and that's R4. And the thing we're interested in is that current there. So what would I do here? This one's a bit trickier, but I can still do it just using voltage dividers and current dividers, I believe. Right? Yeah, so why don't we do this? So the total equivalent resistance for R1, R2, R3 and R4 is just R2, because that's by itself, plus R1 in parallel with R3 plus R4. Okay? So the total current is just going to be Vs. Actually, it's the I drew it the wrong way around. That should be a minus sign and a plus sign. So I'm probably should call that minus Vs on our equivalent. Right. So that's our total current flowing out of the battery, but then I need my I out, and my I out is just going to be the resistance in the other branch divided by the resistance in the other branch plus the resistance in this branch times the total. Okay, and this is I out 2. And then the overall number should be the sum of the two. It's a little tricky because of the upside down Vs, but I suggest if you get a wrong answer, just try and change the sign of the Vs that you use, and that should work that through, and that should work out the right number. You're welcome. The problem 1, the power dissipated. Sorry, I didn't go. Apparently, I missed something in the Thevenin homework. Problem 1. Maximum power. Okay. Right, so let's think about maximum power. Let's just go back to problem 1 back here. I didn't answer that. I should have done that earlier. Apologies for that. Right, so we get our RTH and our VTH, so we can write out our circuit like this, right? So there's our VTH, and there's our RTH, and there's our RL. And I think the question asked for RL equals VTH. And yeah, so it's the maximum power. Remember, maximum power theorem says that RL equals RTH, right? So there's our circuit. the equivalent resistance of that circuit is just 2 RTH, and the current, it's going to be the Norton, well, it's not going to be the Norton current. The current for that circuit is going to be VTH on 2 RTH, right? So the power is VTH times I, which is V squared, VTH squared on 2 RTH, and that should give you the answer. Okay, so you're saying, Joel, you got V squared on R, and that's correct, except the voltage you need to use is the voltage on the load, right? It's not the total voltage. Because we've got RTH and RL equal, the voltage divider equation just says that the voltage on the load is half the voltage, half the Thevenin voltage. So that's where that 2 comes in. Okay?
Yeah, I'm still a little confused why there's an RTH and an RL, and you're using a series circuit to calculate the power dissipation.
Okay, so the whole point of the Thevenin equivalent, right, is to be able to replace this whole circuit, right, excluding the load. R3 is our load resistor, right? The whole point of Thevenin is to be able to replace all of this, Vs, R1, R2, Is, and R4, with this, the Thevenin equivalent voltage and the Thevenin equivalent resistance. And then we can come along and ask questions about power dissipation, because we can forget about the complex circuit. We can use the simple circuit. And we're putting RL back into place, right? We're putting R3 back into place, but in our simplified circuit. Okay, so we replace our complex circuit with the Thevenin equivalent circuit, which just has a voltage source and a resistance, and then we add back in the load that we took out when we did our Thevenin analysis, and then it makes the power dissipation question easy. Okay, does that help?
That makes sense now.
Okay. Looks like I got another question. So for problem 2, part 2, is this in superposition? Okay.
No, that's for homework 6.
For this homework?
No, the Thevenin equivalent stuff.
Okay, so question 2 of the Thevenin, yeah?
Yeah, for part 2, I'm just confused on what exactly they're asking.
Okay, well, it's basically exactly what I was doing, except instead of power, right? So for question 2, again, we've come up with the VTH and the RTH, and what it's asking is, what's VL? What's the voltage across the load once you put the load back? Right, so there's our load. When we did our analysis, we took the load away. we did the analysis so we can replace V1, Vx, V2, sorry, R1, R2, V2 with a Thevenin voltage and a Thevenin resistance. So we do that, and then it's just asking if we put the load back and we connect it to the Thevenin equivalent circuit, what's the voltage, what's the output voltage? So we, and it's a bit, actually this one's a little different because we haven't specified, well we haven't said that it's at maximum power, right? The other question was about maximum power. This one's different because we've got some other value of RL, but it's the same idea. We take our Thevenin equivalent circuit, which is just a voltage source and a current source. We put the load back, and now RL is not equal to RTH, it's something else depending on your question. But we're still interested in what the voltage across the load is. That's the output voltage. And that's just going to be equal to RL on RL plus RTH times VTH, just the voltage divider equation.
Oh, okay, that makes sense. Thank you.
Okay. Okay. I'm about done. That's a little longer than I normally go without a break. So I suppose most of you are done too. I hope. So let's leave it there for today. I have moved homework 7 and lab 7 off till next week. I think this one is due today, homework 6. So please have a go at getting that done. Thank you for your time and attention today. I will talk to you next week.